So now we're going to talk about how to apply Newton's laws. Last class we talked about Newton's laws. What's Newton's first law? Law of inertia. An object at rest stays at rest. An object in motion stays in motion unless acted upon by a net outside force. Newton's second law. F equals ma. Newton's third law. Excellent. Every action has an equal and opposite reaction. Now we're going to look at some of the ways that we can apply these laws and how they affect us. Before we do that, we need to start off with a little bit of science humor. Science humor for you. This is Sir Isaac Newton, who was a brilliant physicist, brilliant mathematician, and an amazing pickup artist. Notice his smooth lines here he used on the ladies. Say, did I ever mention that a body at rest will remain at rest? And a body in motion will stay in motion unless acted upon by outside force. Speaking of bodies, if I said you had a nice one, would you rest it against me? Awesome pickup line. You guys try it sometime. Works out great. Chicks dig science geeks. It's awesome. Okay. Yeah, that's it right there. Okay. Let's look at the elephant feather question. Okay, I go up onto a really tall building and I throw an elephant off of it, and at the same time I drop a feather off of it. The question is, as they're falling here on Earth through the air, which one experiences a greater amount of air resistance, the feather or the elephant? Good questions. Those are all good questions. Okay, let's take a hand-raising vote thing. How many of you believe that the feather experiences a greater amount of air resistance? 1, 2, 3, 4, 5, 6. How many of you believe that the feather experiences a greater amount of air resistance? I'm sorry, the elephant. The other thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. Some of you, how many of you don't have any idea? Excellent, that's 1. We still haven't gotten everybody. How many of you just don't care to vote? Okay, thank you very much. Okay. We will talk more about this, and by the end of this, you will figure this out, and we'll know it, okay? Yes. So, Newton's second law. Okay. Newton's second law is a very, very simple equation, you guys. F equals ma. The thing that you will struggle with Newton's second law is figuring out what F we're talking about. Not what the F we're talking about, which force we're talking about, okay? The net force is critical. And when we say net force, we mean add all the force vectors acting on an object, and the resultant, the thing you end up with, is the net force. Now, Newton didn't really create his second law this way. When Newton actually came up with his second law, he talked about this thing called quantity of motion, which we now call momentum, and we represent with the letter P. This is truly Newton's second law the way he presented it, that force causes a change in momentum over a change in time. We will talk about this a little bit more when we get to momentum, but since we haven't talked about momentum yet, we won't really touch on it much more. But I just want you to recognize that's the way Newton described his second law. Let's differentiate between mass and weight. We did this last class, but let's do it again to make sure we start figuring it out. Who feels like they have a good definition for what weight is? What weight is? So.
When gravity acts on mass,
Okay.
I don't. It's not very good definition, but
Gravity acting. Okay. And Max, you want to add to that?
Weight is mass and gravity. Well, weight is mass.
Michaela. Excellent. Okay. So you guys are all tiptoeing around it. Michaela nailed it right on the money. The weight of an object is the force acting on it by gravity. It's the force of gravity acting on an object. We call that weight. Okay. And since force equals mass times acceleration, the weight of an object equals mass times the acceleration of gravity, which we've been representing with the little letter g. So weight equals mg. And it will change depending on where you're located. One of my classic get-rich schemes, the way I was going to stop being a teacher and go and drive a Ferrari and live on Red Mountain, was my new weight loss program. You give me 50 million bucks, I send you to the moon, and you instantly lost weight, even though you didn't do any exercise, and you can still eat donuts and hamburgers. And you will weigh less, because weight depends on where you're located. It was a bummer. No one signed up for it. Yeah, I know. Okay. What is the unit we measure weight in? Pounds here in America in science class, newtons, because weight is just force. And a newton is equal to a kilogram times a meter per second squared, because force equals mass times acceleration. So a newton is a kilogram meter per second squared. It is the amount of force it takes to accelerate 1 kilogram, 1 meter per second squared. Eli. Okay, so you go to the grocery store and you want to buy some apples, and you know they cost 60 cents a pound, and you throw a bunch of them on that scale there at the grocery store. Someone's calling me. Okay, so you're at the grocery store weighing your apples. You put them in that thing, you know what I'm talking about? The bucket there, and the spring hangs down, and it tells you how much they weigh? Yeah? That's called a spring scale. Is that measuring weight, or is that measuring mass?
Weight.
And how do you know?
Because it says 60 cents a pound.
Okay, but why? But it could just as easily be measuring mass. So which is it doing? Is it really measuring weight, or is it really measuring mass?
Weight. It's weight. Well, it depends on what your scale is, because I don't know.
Because it's pulling down.
No,
Apples are pulling down. It doesn't how hard the apples are being brought.
So if you took that scale, if you took that same scale and you took it to the moon, would it say the same thing? No, because it's a spring being stretched, and it's actually measuring the force of gravity on it. It is measuring the weight because it's how hard it's pulling down. And if I took it to the moon, it wouldn't pull as hard, and it would say I didn't have 2 pounds of apples. It would say I have 1/3 of a pound of apples. Okay, what do we use then to measure mass? What truly measures mass? What device does that? Scale in a doctor's office. Think about that. When you go to the doctor's office and they weigh you, right? You stand on that thing, and what do? They slide the little bar, and notice they're getting it to balance. It's called a balance. And you guys have used balances before, probably in your science classes, where you put something on a little pan and you twist some dials and move some weights to balance it out. That truly measures mass. Because think about a basic. So a spring scale actually does measure weight, and not mass. When you go a typical bathroom scale that most people have in their house, that actually is weighing you because you're compressing a spring, and it would weigh differently if you went to a different planet. So let's be real clear about this idea of weight and normal force. Weight and normal force. What direction does weight act? And what do you mean by down? Towards the center of the earth specifically, okay? It's the gravity of the earth pulling you towards the center of the earth. We talked about this definition last time. What is force normal? When I talk about a normal force, what am I talking about? Okay. It's a force that a surface exerts perpendicular to itself. And it's in IB, they'll often call it a normal reaction. It's a reaction force like Newton's third law. If I exert a force downward on the floor, it exerts a force upward, equal and opposite. One of the things to consider is that if I have a horizontal surface and an object resting on it, it has weight, and if it's not doing anything or going anywhere, the force normal is going to be equal and opposite to the weight. But that is only true on a horizontal surface. If my surface is no longer horizontal, notice that the weight acts towards the center of the earth, and my force normal is still perpendicular to the surface that it rests on, and they are no longer equal and opposite. You could add those vectors, and notice now that if I take force normal plus my weight, I'm not in equilibrium anymore. I have a net force, and my net force is the resultant. There's my net force, and therefore my crate is accelerating down the ramp. Okay?
Last class, you were talking about like if you would punch.
Okay, let's see. So let's look at a question here. Okay, you got a 2 kilogram block of iron. Does it have twice as much inertia as a 1 kilogram block? I want you to look at these 4 questions, actually. Talk to your friends, talk to your family, think about them. You have approximately 14 and a half seconds, and then we'll discuss what the answers might be. All right, you've had a moment to think about it now. Let's discuss it. I'm going to skip the first one for a second, okay? Because we've talked about inertia as a law, but we haven't really talked about like what inertia is in terms of an object. So we'll come back to that. Let's look at the second question. Does a 2 kilogram block of iron have twice as much mass as a 1 kilogram block of iron? Because kilograms is mass. So if I have 2 kilograms of anything, it's twice as much mass as the 1 kilogram. Great. Yes. Does it have twice as much volume? And give me an example.
So like,
Because they're both made of iron. So give me an example of how the volumes might be different.
If there was a lead
if
core.
one's like,
They're both made of iron.
one's a cube and the other one's a cube.
One's a liquid and one's a gas. One's a liquid, one's a gas. Or one's a liquid, one's a solid.
Okay, so we could have different states of iron. Excellent. If they're solid blocks, they're going to have the same volume. If they're solid blocks at the same temperature, they're going to have the same volume. But if you make one like hollow, someone mentioned last time, what if one's like a hollow sphere? You can make it different sizes. That's interesting. The phase changes we haven't talked about. That's a possibility too, certainly. And that would, okay, so not necessarily. I'm going to say not necessarily on that one. How about twice as much weight? Always?
Well, if they're both.
If they're both in the same.
Excellent. If they're both in the same gravitational field. If they're both on Earth, yes, 2 kilograms will weigh twice as much as one. But if I take one and put it somewhere else in space, it's going to weigh a lot different than the other one. Great. So I'm going to put not necessarily, but at the same location, yes. So let's talk about this idea of inertia. We use the word inertia to describe Newton's first law. And basically we said it's an object at rest, an object in motion, blah, 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 blah. The idea of inertia is this. Inertia is the property an object has that determines how much it resists change. Inertia is the property that resists change. If something has twice as much inertia, it takes twice as much force to make it accelerate. So does a 2 kilogram block require twice as much force to accelerate as a 1 kilogram block? Yes, it does. Yes, it does. Okay. So mass is the thing that determines inertia. And therefore, something that has twice as much mass will be twice as hard to change its motion. Okay. Friction. Now, friction is something that really exists everywhere. In a lot of the problems we do in this class, we're going to ignore it because it makes our lives a lot easier, but we're not always going to ignore it. And friction is a force that occurs when something between any two objects that are in contact with one another, and it generally is a force that opposes motion. Okay? It is force that opposes motion. Come on. Opposes motion. Opposes motion. It opposes. Now, all this stuff comes up at once. That's not what I wanted to do. No. A force that opposes motion. Here's the idea. You've all experienced it before. Here's the general idea. Here's a big object. And I'm pushing on it. Big object sitting right here, and I walk up and I push on it, and it doesn't move. Why doesn't it move? Not because of inertia, because of friction. If there was no friction, and this object was enormous, it was the Empire State Building, and there was no friction, I could move it. I could walk up and flick it and move it, right? So it's not the inertia that prevents it. The inertia determines how fast it moves, but if there's no friction, I can move it. So let's say I walk up and I push on it with 10 newtons, and it doesn't move. What has happened? So there's friction pushing back. And is there more friction? So let's say there is more friction. There's 20 newtons. Does that mean... Okay, because what happens if there's more? It's accelerating towards me, and that doesn't happen, right? You push on it and it flattens you? No. Okay. So friction is this weird thing that knows how hard you push. I push with 10, it pushes back with 10. I push with 20, it pushes back with 20. And it always matches it as long as the object is not moving. But then think about what happens. At some point, I push hard enough, and it starts to move. And once it starts to slide, from your personal experience, so static friction is the friction that exists when two objects are stationary relative to one another. Kinetic friction is the friction that exists when two objects are sliding past one another. And which one, from what we just said and from your experience, which one is stronger? Static, because it's easier to keep something moving when it's sliding, right? Static friction is stronger. Let's think about this in something that's important to your lives every single day. Driving your car, riding your bicycle, riding your skateboard, whatever it is that has wheels. You're going down the road, and a little kid comes running out from the sidewalk chasing his ball into the street. And you're trying to stop your car. Do you stop faster if the wheels are rolling or if the wheels are locked up and skidding?
ABS.
Okay.
It depends on how, it depends on how.
When your wheels are rolling, is the contact between the wheel and the ground stationary or moving? When your wheels are rolling, is the contact between the wheel and the ground stationary or moving? It's actually stationary. If you think about when a wheel moves, the actual contact is not sliding. It's stationary relative to the ground. That's why the wheel is rolling. When your wheel is locked up and not rolling, it's skidding across the ground, and that is not stationary. That's sliding. You with me? You just told me that stationary friction is stronger than sliding friction. And it's definitely true. Your wheels can exert more force if they're rolling over the surface than if they're sliding over the surface. And this is why they invented anti-lock brakes. ABS brakes make sure that when you hit the brakes as hard as you possibly can, the computer controls your little calipers in there so that your wheels continue to roll as you come to a stop. Because as soon as you start skidding, you will go farther. You will stop less rapidly.
Does the e-brake stop us from moving?
So let's look at the okay. Let's look at the mathematics of friction. Pretty simple stuff. Basically, if I want to figure out how much friction I have, there's two things that will determine it. The surface. Smooth surfaces have less friction. Rough surfaces have more friction. And how much weight or force I have on that surface. So mathematically, it looks like this. Okay, the force of friction equals mu times the force normal. Okay? The force of friction equals mu, which stands for the coefficient of friction. This is a Greek letter mu, which stands for the coefficient of friction, which basically is determined by the surface. It tells me something about the surface. It tells me how sticky or how slippery the surface is. A sticky surface has a higher or larger value for mu. A slippery surface has a lower value for mu. And then this is force normal. So that's it. If I know the force normal and the coefficient, I can figure out how much friction I'm going to have. Okay?
Wait, isn't that
Okay.
also the something like that?
It is. Yep. Kinetic. So in here we're talking about kinetic friction. Now, no, except for this. Here's the thing. It's a great question. Here's the thing for static. Remember, static varies from, like if I have an object sitting there, if I'm not pushing on it, there's no friction. But if I push with 5, it pushes back with 5. If I push with 10, it pushes back with 10. So static varies from 0 up to a maximum value. And the maximum value of static will be calculated exactly the same way. Okay? So it looks like this. Keeler, what's your question?
Does that work when it's like on an incline too?
Yes. But on an incline, the force normal is not going to be the weight. But it's the force normal that determines. If we're on a horizontal surface, we're always talking about the force normal. Sometimes the force normal is equal to the weight, but not always.
Not an incline.
We'll talk about that. We'll use vector components to do that. Okay. Let's look at some coefficients of friction just for fun. You don't need to memorize these. But here are some coefficients of friction. And notice you have a different coefficient for static friction than you do for kinetic friction. And the coefficient for static friction is always greater than kinetic friction because static friction is potentially stronger than kinetic friction. The maximum value of static friction is higher. So wood has a pretty high coefficient of friction. It's pretty sticky stuff. Ice has a low coefficient of friction, particularly once you start sliding on it. Okay? Metal, pretty good. Rubber is pretty darn sticky. That's why we make shoes, soles of shoes out of rubber, or climbing shoes out of rubber, right? Rubber on other surfaces can get up to 4. That's huge. Okay? But notice like ball bearings, almost no friction at all. This is one of the reasons why we use ball bearings in situations where we don't want much friction, in like wheels, skateboard wheels and things, right? And in your joints, you know, God was thinking about friction when God made your joints, right? You got knees and elbows and shoulders, and they're very, very frictionless, very low coefficient of friction. I don't know, just to make us complain. Okay. Some of you are visual learners, so here's what I'm trying to express to you. You have two kinds of friction, static and kinetic. Static is a reactionary force. If I push with 10 newtons, static friction pushes back with 10 newtons. Okay? If I push with 20, it pushes back with 20, up to some maximum value that will be determined by the surface and by the object resting on that surface. In this case, that maximum value appears to be about 39 newtons. So if I push with 39 newtons, my object doesn't do anything. But if I push just a little bit more, suddenly I've overcome static friction and my object starts to slide. And when it slides, I enter the realm of kinetic friction, which is less than the maximum value of static friction. Does that make sense? Okay?
What's F?
All right. All right, you guys calculate the acceleration. If you push with 20 newtons horizontally on a 2 kilogram block, which is on a horizontal friction-free surface, please calculate the acceleration of that block if you push with 20 newtons and it has a mass of 2 kilograms. What do you get? And how did you do it? F equals ma. 20 equals 2a, therefore a equals 10. Great. Now, what if I do have friction? And let's say I have 4 newtons of friction. Now how fast does it accelerate? Yeah, but these are easy vectors to do. So what do you do? No. No.
16.
What's the acceleration now that there's, what's that? 16. No, you're getting closer.
Oh, yeah. Then it would be, yeah.
8 meters per second squared. Okay.
Because the
Here's my object.
would be 16.
I'm pushing with 20 newtons. Friction's pushing back with 4 newtons. What's the net force? 16 newtons. 16 divided by 2 kilograms, 8 meters per second squared. Okay? Yeah? Okay. Air drag and terminal velocity. Let's think about this for a second. Okay. Good. Air resistance, which is sometimes called drag, is just friction as you move through the air. That's all it is. It's friction between you and the air. What are the 3 things that determine how much air resistance you experience? The surface area you have moving through the air, that's 1. How fast you're moving through the air is 2.
How high you are, because you could have a really scary body.
Well, let's think about altitude here. What is altitude really having? What's it really doing? The density of the air. Great. So it's going to be really altitude and temperature and all that other stuff. Those are the 3 things that determine air resistance. If you're not moving, how much air resistance do you have? 0. And the faster you go, the more air resistance you have. The other thing that affects it is the surface area you have going through the air. And you already know this intuitively. You already know this. Because when you're skiing or snowboarding and you want to go faster, what do? You get smaller. You get in a tuck. You get in a tuck and make yourself smaller and you go faster. If you want to slow down, you stand up, you open up your jacket, you look like a tourist and go, wahoo, and you slow down because you're all big, right? Smaller and bigger makes a difference. And then the density of the air would make a difference as well, okay? So those are the things that affect air resistance. So let's go back to our little elephant and feather question then, okay? And first of all, let's imagine I go to the top of the building and I take away all the air. So we're in a vacuum. And I drop the elephant and I drop the feather. Who hits the ground first? Same time. That's what Galileo told us, the law of falling bodies, that they'll both fall with what acceleration? 9.8 meters per second squared. That's assuming there's no air resistance. But we know in most cases there is air and there is air resistance. So let's look at it. Which one of these objects Weighs more? Which one has more gravitational force acting on it? The elephant, because that's what weight is gravitational force. So the feather has a little bit of gravity acting down, and the elephant has a whole lot of gravity acting down. Okay? And I drop them. Right when I drop them, when they're not moving, there's no air resistance, and they both accelerate at 9.8 meters per second squared. Very quickly, because of its speed, the feather experiences air resistance equal and opposite to its weight. And what happens at that point? We're not in a vacuum anymore. Equilibrium. Who said that? Equilibrium. And therefore, what's going on? It's moving. It's not holding still. It's moving with a constant velocity now. What we call terminal velocity. Okay? The thing that's holding still is its acceleration. It's no longer accelerating. That's what's holding still. The elephant, on the other hand, it starts to fall and it experiences a little bit of air resistance. Is there a net force acting on it? So it's still accelerating. And it goes faster and it gets more air resistance. Is it still accelerating? And it will continue to accelerate until the force of air resistance is equal and opposite to its weight. And then we have terminal velocity, and it is going to be a much higher velocity than the feather. And so back to our original question, kind of, F equals ma more than anything. Which one's experiencing the greater force of air resistance? The elephant is. Even though it's falling at a faster rate, it's experiencing much more air resistance. Okay? Driving for a second. Okay? So you jump out of an airplane. And forget about an airplane. And Cameron, we'll talk about your situation here. Let's say you jump out of a helicopter, and there's no wind. We'll keep it simple. So you're stationary. You jump out of a helicopter. Immediately, you've got your weight acting down, and right when you jump, how much air resistance do you experience? Zero air resistance, because you're not moving yet, right? And so is there a net force acting on you? Is there a net force acting on you? So then it's down, and you accelerate downward at 9.8. As you go down, you start to experience some air resistance. There's my air resistance. Is there a net force acting on me? Yes. Therefore, I'm accelerating, but am I accelerating as fast as I was? Your acceleration is decreasing because now my net force is getting smaller. I've got this much down and a little bit up, so my net force is decreasing. And I go faster. And as I go faster, I get more air resistance. And now my acceleration is less. And at some velocity, the force of air resistance will equal the weight. And then what has happened? Terminal velocity, equilibrium. I'm no longer going faster. Unless I change my body orientation. And good skydivers can do that. They can tuck in, they can aim down, they can go faster. You've seen it all in James Bond movies and stuff, right? Where bad guy jumps out with the parachute and the good guy jumps out with nothing and chases him through the air and grabs him and steals the parachute, and it's awesome, right? You can do that by changing your orientation. Now let's think about the parachute. Okay, so we're in equilibrium, we're going at terminal velocity, life's great. If you actually close your eyes, you would not have a sensation other than the air moving past you, but it wouldn't be, you wouldn't have a feeling of accelerating. You would feel exactly the same as standing still because you're in equilibrium now, except for the air moving past you, right? Exactly. It's acceleration that makes your stomach kind of go woo, but like when you're at constant velocity, it's pretty just normal. You know what I mean? And so then you pull the parachute. Okay. Okay. Let's think about what happens. What have I changed by opening my parachute? The surface area. I've made my surface area larger, which has done what to my air resistance? Now look what happens. Suddenly I have a much bigger air resistance. What direction is the net force on me? Up. What do? I accelerate up, which means I slow down. And as I slow down, my upward force gets smaller and smaller and smaller until it matches my downward force, and then I have a new terminal velocity, which is much slower than it used to be. Okay. Okay, guys, answer this question. Answer this question. Oh, wait, there's no question. Try that one. Just want to make sure you're awake. Make sure you're paying more attention than I am. Okay, now answer that question. It would be 0. What makes you say it's 0? Constant velocity. Technically, this is not terminal velocity. The idea of terminal velocity usually deals with falling things. But yes, it's at a constant velocity, therefore no acceleration. Therefore, what is the force of friction? What is the air resistance on this jet? 80,000 newtons. Even though the jet's pushing as hard as it can with 80,000 newtons of force, okay, it's not accelerating because there are 80,000 newtons of air resistance. You with me? Okay. Because an object in motion stays in motion unless acted upon by no. So,
When you start your car,
yeah.
first step was to come up.
Okay, the last thing I want you to think about, and you'll have to do this on some of your homework problems, is you have to remember that force is a vector, and you have to add force as a vector. So let's look at a simple scenario here where I have an object that weighs 10 newtons. If I hang it from a single scale, what will that scale read? 10 newtons. If I hang it from 2 pieces of rope that are going vertically up, how much tension will be in each rope? Because the upward, as long as it's stationary, as long as it's in equilibrium, the upward force has to equal the downward force. What if instead of this, however, I have my cables going like that? Will it be more or less than 5 newtons?
It'll be more than 5.
It'll be more than 5 newtons. It'll be more than, and here's why. Here's how you're going to solve problems like this. Assuming that you are given some angles, remember that every vector, let's call this f, can be broken into x and y components.
You don't know what the X component is.
In this case, I don't know it, but I do know what the y component is. If I have 2 cables and the angles are equal, this is going to be 5 newtons. And if I know this angle, I can now solve for how much tension there is in the cable. All right? You'll have to do that on the homework. So let's see what we had to say about that. So 2 scales, we just kind of talked about that. Restoration forces, simple harmonic motion, we'll get into that later. Pendulum swings and springs. We'll get into that later. This is the last thing I kind of want to talk about. Inclined planes we're going to talk about in much more detail at a later time in our next unit, actually. But I want you to see this. Notice now we have an object on an incline. There's 3 forces acting on it. Okay? There's 3 forces acting on it. One force is gravity, which always acts down towards the center of the earth. The other force is the normal force. Notice it's still perpendicular to the surface. And the third thing is friction. In this case, if I add up all 3 of these vectors, if I take the force normal plus the weight plus the friction, and they add up to 0, what do I know is happening to my object? And what's it doing? Not moving, or what? Constant velocity, okay? If, however, I add up my 3 vectors, here's the force normal, here's the weight, and here's friction, well, notice now they don't add up to 0. I have a net force, and here's my net force right there going down the ramp. What's my object now doing? Accelerating down the ramp, okay? So we'll get into forces and vectors in multiple directions shortly, but right now we're just going to try to practice Newton's laws, usually with vectors in the same direction or in static situations where things are hanging by cables.